Hello, my name is Fernando Trevino, and today we're going to be talking about the suffix tree construction with Okunion's algorithm in O time. For this, let's first talk about why we want to do this. So, one of the problems we can solve with this algorithm is given two strings x and y of total length n over a constant size alphabet, show how to compute the longest common substring in O time. So for this we have a couple examples. So let's say we have string 1 being ABCAD and string 2 ABCE. Well, the longest common subsequence is ABC. Similarly, for these two strings, we'll just have B and C, and similar thing for example 3. Before we start, we have a couple rules that we need to cover that we're going to keep using along the algorithm. So rule 1 says each new character will need to be added to each leaf. We actually don't need to worry about this rule because we have a special trick called label compression that will be doing this automatically for us. So it's good to know it, but it's gonna be done automatically. So don't worry about it. For rule 2 and 3, we need to, that's gonna be the main loop. So we'll ask while remaining is just a variable that we're gonna have. While remaining is not 0, and we're gonna start from the active node, and we're gonna advance length steps. Length is another variable that we're gonna have. We'll check if the current index x exists. For that, we can only answer yes or no. If the answer is no, then we fall into rule 2 territory, for which rule 2 says that we're going to create the path. This may include that we might need to create a new node, and we will decrement remaining by 1. But if for the previous statement, the previous question, we enter yes, then we will fall into rule 3 category. So rule 3 says that we'll take note of the active node and edge, and we won't decrement remaining just like rule 2 does. Instead, we'll ask another question. If the active node is different, then change it back to root. Don't worry if this doesn't make sense, but we'll see more examples once we walk through the algorithm. So we'll change it to root, and we won't change the active edge either. But if we're in a different node, then we'll increment active edge by 1 and decrement length by 1. Then we'll continue with the main loop. So on each cycle of the main loop, we will increment an end variable in a remaining variable by 1. We have another special rule which is called the suffix length rule. Suffix link, sorry. If in a given cycle a new node is generated, it will be linked to the root node unless a subsequent node is generated during the same phase, then it will be linked to the new node. So once we make a new node, we'll point it to root. Then if we continue the algorithm in the same loop, we make another node, then we'll fix the previous one to point to the new one instead of root, and then point the new one to root. Well, I know I just said a bunch of nonsense with the rules and all that, and it doesn't really make sense, but I hope this is going to clear out while we walk through the algorithm. So now that we start, we can see on the left, top left, that we have some variables and their content, their value. This side we have the string that we're gonna use to create the suffix tree, the index, and the current cycle that we are in. So right now, end is pointing to 0, That means the index is at letter A. We're currently in this cycle. Since we started a new cycle, remaining will increment by 1, so we need to ask the question. So while remaining is not 0, which is not, starting from the current node, so the current node is root, so we can see it, and advancing length steps, so length starts at 0, so from root move 0 steps in the direction of the active edge, 0, so we're not really moving because length is 0, so we're still in root. Check if the current index x exists, so the current index is A, and no, I do not see any A connected to root. So since the answer is no, we'll take action according to rule 2, which says add it. Since rule 2 was applied, we'll need to decrement remaining to 0, and then since remaining will be 0, then we will advance to the next cycle. So now we can see remaining has decreased to 0. We have added A, and I want you to note that this notation below here reads as starts from 0 and ends at this location. So end is variable, which is currently 0. So that means the string from 0 to 0. So from 0 to 0, that's just A. So this is our visual representation of this path. So this one is not necessary to save in an actual implementation. This is what we're going to save. But for us, it's easier to see the letters or the string in the path so we can follow it a little more easily. Let's move on. So notice that since we reached 0, we cannot ask the question anymore. So we'll go to the next cycle and remaining will increase. So remaining increased and increased as well. And we advance to the next index. So since remaining is not 0, we'll ask the question again. So starting from the current node, root, advancing length steps, 0. Check if the current index is x. So no, there's no b's in this place. So we'll need to add it as rule 2 just said. So, but before we add b, I want to point out what happened with this b. Why did it just appear out of nowhere? So remember this reads as from 0 to end. And what is end now? Well, end just changed to 1. So from 0 to 1, that's AB. Here's AB. So it's written from right to left just so that we can see which character comes first. So A was first, then B. So if I had it in this side, it will be A, then B. So reading from left to right. I know it's a little confusing, but hang out with me. It's going to make sense later. So let's go ahead and add B. So now we have it. We decremented remaining to 0. And we have, since remaining is 0, we don't have anything else to do. So we'll need to advance to the next index, increment end, and increment remaining. So I'm not going to walk through this step by step since I think we're getting the hang of it. So once again, remaining is not 0. We ask the question, do we have C in root advancing length steps? So no, we don't have it, so we add it. And notice that and was nice enough to append the C to each of the other paths. So far nothing interesting is happening. We're just adding the letters as we're seeing them. But now A is going to appear, so the answer is actually going to change. So since we're moving to the next cycle, remaining is back to 1, we ask the question, can we see A from root advancing length steps? Well, I do. Here it is. So the answer is yes, and now we're falling into rule number 3. So rule 3 is saying that we'll need to increment length by 1 and take note of the active edge. So since we found A on this direction, we can see that the edge is if we take the 0. Not the 2, not the 1, but the 0. So we'll save the 0 in this place, and the active node is still root. We don't have any other nodes so far, so that's going to stay as it is. And of course, increasing length, we'll advance to the next index, and we'll leave remaining as it is. So we won't modify this one. And because we're going to the next cycle, it's going to increase by 1 again. So well, before we move on to that, I just want to show I increase length to 1. So now we move on to the next one. Remaining is now 2. Note that from the root, advancing length steps, we are in A. So now we ask, is the next character, D, in that position? So the next character is B. So no, it's not D. Therefore, we fall again into the rule 2 category. We'll need to add it. So in this case, where do we add it? Do we add it on the root, or do we add it right after A? Well, we want it to be right after A, but there's no space because we already have this B. So we'll need to create a new node, like so. So the original was from A, B, C, A, D, and the new one is just D. So AD so far. Notice that this AND is being nice enough to update our string on every single cycle, and A doesn't need the AND anymore because we just want to say it was from 0 to whatever the however far we were already. So in this case, from 0 to 0, just representing A, and we have this nice thing. You'll notice that we have this special connection that I marked in orange. So that's a link that, according to rule 3, we every time we add a node, we need to create a link pointing to root. Then we will modify this link if we create another node in the same cycle that then that link will point to the new node, and the new node will point to root. In this case, we're not there yet, so it's just going to point to root. Since we added the node, we decrement length by 1, and we will increment the active edge by 1. So remaining is not 0 still, so we'll need to ask the question again. So if we go from the active node, root, length steps 0, in the direction of the active edge 1, well, this is the active edge, but we're advancing 0, so we're still in root, and we're looking for the character D. Well, this one is A, this one is B, this one is C. There's no D's, so we'll need to create it as rule 2 indicates. So we'll add it, decrement remaining, and let's see how that looks. So here it is. We added D, and nothing else that we can do here. We decrement remaining, so now it's 0, therefore we cannot ask anymore, so we'll move on to the next step. Remaining will increase and will increase, moving our index one more step. So here we're gonna ask again, so do we have A? Well, from root advancing 0 length, we can see it, so we do have it. So according to At roll 3, we'll increment the length. We'll take note of the active node and edge. Still we're in root, and the active edge is 0. So nothing else we can do. Of course, you'll see that A was appended to all of the path because of our variable. But that's done automatically. We don't need to do anything special for row 1. Let's move on to the next step. Now we have B, so we asked again, from root, advancing one step for length, can we find a B? So we were in A, if we advance one more, we had a B and a D, so B is present, therefore we fall into row 3 again. We will increase length by 1, so this is going to turn into 2. We increase active, we take note of the active node, which is now N1, and the active edge is 1, so we'll take note of that. And we will leave remaining as is, so it will increment once more. Let's move on to the next step. Here, we ask the same question, which is the same from before. In this case, we were at B, and we asked, is the character C following B? In this case, it is. Therefore, we fall yet again in row 3. So we do the same thing. We increase length. We take note of the active node, the active edge. We'll leave remaining as it is. So it's going to keep incrementing. And we advance to the next cycle. So in this case, we finally reach the last step. We're in the last character, and we ask the question. Starting from the current node, it was N1, and advancing length 2, in this case. Can we find the character E? Well, we didn't have it, because it was B, C, A, D, and so on. So we had to fall into rule 2, which says add it. In this case, we couldn't add it without adding a node, so we add the node to be able to have the new path for E. And since rule 2 was applied, we'll decrement remaining, so this is going to turn into a 3. And because a new node has been created, we'll check if the active node is root. Well, in this case, it is not. It's N1, so we'll change it to root instead of incrementing the edge by 1, and we won't decrement length just yet. So since it's a new node, we'll point it to root as our temporary link, and note that if we create another node in this step, we'll need to fix this length. So let's see how that looks. So we have decremented remaining, and we're basically stuck because we can't go to the next cycle because remaining is not 0. Therefore, we need to ask the question once again. So from the current node, root, advancing length steps in the active edge direction. So active edge is 1. We'll advance two steps, 1, 2. So we're in C. Do we have an E? We do not. So we fall again in rule 2, which says add it. So we'll need to cut this place into 2. We'll have BC, then this string, and then just an E. Just like that. And because we have created a new link, we need to fix a couple things. So remember that we had a link from N2 to root. Well, that has been updated to point to N3 because it's a new node that has been created in the same step, and N3 is going to point to root. Then active node is root, as we can see, so we will increment the active edge by 1, and we will decrement length by 1, so it's going to be 1 now. So we have done all those things. Now we're still stuck because remaining is not 0, therefore we need to ask the question once again. So from the current node, root, advancing in the direction of active edge 2, here's 2, we'll go one step, so we end up in C again. We ask, do we have an E? Well, the next character is A, so no, we do not have an E, therefore we need to create yet another node down here that is going to split this string, and notice that this edge is going to connect to the new node, just like that. So the edge connected to the new node is pointing to root, as we have done before. We decrement length, we increase active edge, and since we apply roll 2, we decrement roll 1, remaining to 1. So are we done? We're not actually, because remaining is still not 0. Therefore, we have yet another question to ask. We ask the question. So since from root we advance 0 length, and there's no, we asked if we have an E, so we didn't have this edge, so there was an A, a D, a B, and a C, so there was no E. For we need to add it according to roll 2, so just add it, we decrease remaining by 0, and there was no node created, so we don't need to fix any of the pointers, and we move on to the next cycle, which is outside of the array. Therefore we're done. We don't have any more cycles to work with. We have constructed our suffix tree and we're ready to use it. So before we even use it, we need to make sure that we actually get the correct suffix tree. So let's say these are all the suffixes possible for this string. So let's see if we can actually find them in the suffix tree. So let's start with the smallest. Start with E. So from root, do we have E? We do. It's right there. So what about CE? Well, CE, there it is. BCE, BCE, and then ABCE. Here's A, B, C, E, then D, A, B, C, E, A, D, A, B, C, E, and so on. You can prove it to yourself that all of them are here. So now, going back to the original question, now we wanted to find the longest common subsequence of two strings. So let's say, excuse me, let's say our two strings are ABCAD and ABCE. Let's say that D and E is a special character that they won't have, so we can just concatenate them and we'll have the original string that we were using to construct this suffix tree. So if we construct the suffix tree of the two strings that we have in question, then we'll end up with something like this. And now we need to see if we can find the longest subsequence. So how can we do that? Well, if you look for all the nodes, N2 and 1 and 3 and 4, that end up with a leaf Basically, this one is a leaf. That's the end, basically. This one is not a leaf because it's pointing to another node, but this one is. We have an end, right? So if we find all of those and we check, where is the initial index coming from? So in this case, this one is coming from 8. So 8 is this guy, which is clearly coming from string 2. We'll say, okay, well, this node has some part of string 2, and then this 3 is coming from this A, which is clearly coming from this A, from string 1. Therefore, we can say that this node contains information from string 1 and string 2. Therefore, anything before that came from both of them. So we can see that B and C is a common substring from S1 and S2. So we're close. We're not there yet because we don't know if BC is really the longest subsequence. So since we have the basis, we'll repeat that process with the other ones. For this one, for example, we can see 8 and 3. So C is a subsequence as well that they share, but it's not the longest one. BC was better. So let's see this guy. So 8 and 3 again. And the sequence is ABC. Therefore, we have checked all of them. ABC was the longest one. So that must be the longest common subsequence that we were looking for. And that's it. That concludes the algorithm. This is how you find the longest common subsequence using suffix trees and construct them in linear time. Thank you.